Scatter plots. Use the data below to find an equation for predicting birth weight from gestation. So the birth weight will be the y variable, gestation is the x variable. Usually if you think one variable may cause or affect the other variable, then the variable doing the affecting is the x variable. In this case, the x variable, we're going to call that gestation, or the length of pregnancy. Okay, so we have some data here. Quincy was gestation, or the length of pregnancy for Quincy was 39 weeks, birth weight 104 ounces. Rochelle, gestation 40 weeks, birth weight 100 ounces. Sophia, gestation 32 weeks, birth weight 64 ounces, and so forth. So we want to make a graph to sort of see if we can describe the relationship between gestation and birth weight. Okay, so the x variable will go left or right. A y variable goes up or down. So for Quincy, 39 weeks, birth weight 104 ounces. So we'll go 39 to the right and up 104. Okay, so let's see if I can try to make this reasonably accurate here. Up 104. Let's see if this is 104. 100 is about 45 millimeters. Okay, so anyway, 39 to the right, up 104. Something maybe about right here. And then Rochelle, 40 weeks, gestation 100 ounces. So that's 40 to the right, up 100. So maybe about right there. Sophia, 32 weeks, 64 ounces. So 32 weeks, 64 ounces. So maybe about right here. And then we have Tyrone, 41 weeks, 120 ounces. 41, 120, maybe something like that. Ursula, 38 weeks, 92 ounces. 92, maybe about right here. Vincent, 40 weeks, 110 ounces. Maybe about right here. Wendy, 42 weeks, 122 ounces. Xiao, 38 weeks, 96 ounces. Um, 41 weeks, 100 ounces. And Zelda, 39 weeks, 112. 39, 112. I don't, probably in here somewhere. Okay, so that's our scatter plot. And if you use graph, I didn't use graph paper here. If you use graph paper, you could probably be a little more accurate than I am here. And we want to. So, what does the scatter plot tell us about the relationship between um, gestation and birth weight? Well, it looks like, on the average, it looks like it goes up as you go from left to right. The length of the pregnancy is increasing, and it looks like the birth weight is also going up on the average. So it looks like they're somewhat close to a straight line. So I could show you some graphs here. So if the dots are spread out all over the place, that's little or no correlation. And if they're somewhat close to a straight line, that would be a moderate with a positive slope. It goes up as you go left to right. That's a positive, moderate positive correlation. If they're even closer to a straight line, there would be a strong positive correlation. And if they're exactly on the same straight line, it's a perfect correlation. It's deterministic rather than statistical. If you could also have little or no correlation if you have like this example here. There's a pattern, but it's not a straight line type of pattern. You have a negative slope. The dots are going down as you go from left to right up to a point, and then they start going up again. So they kind of so that's another way you could have little or no correlation. This is a moderate negative correlation, somewhat close to a straight line with negative slope. It's going down as you go left to right. Strong negative correlation, or deterministic perfect negative correlation. The correlation coefficient, we'll compute that later at a different lecture. We'll compute the correlation coefficient, but it's always going to be between 1 and -1. So if it's a strong positive correlation, it's going to be close to 1. If it's the correlation coefficient R, we use the letter R to represent the correlation coefficient. It will be close to -1 if it's a strong negative correlation, or close to 0 if there's little or no correlation. And we'll get into how to compute the correlation coefficient later. Okay, so this is sort of a summary about the correlation coefficient R. Always between -1 and 1. Measures how close the dots are to a straight line. The sample correlation coefficient R is an estimate for the unknown population correlation coefficient. If you switch X and Y, the correlation coefficient doesn't change. If X is related to Y, then Y is related to X. If you change the units of measures, R doesn't change. It just tells the relationship between the two variables. So if we had measured let's say days and pounds instead of weeks and ounces, so if we measured the length of pregnancy in days and the birth weight in pounds, it's still it's not going to change the correlation coefficient. It's still that just tells you whether it tells you the relationship between the variables. So if a pregnancy is long in days, it's going to be long in weeks also, and vice versa. If birth weight is high in ounces, it will also be high in pounds. If it's low in ounces, it will be low in pounds. So the unit of measure is not going to affect R, the correlation coefficient R. The sign of R is always the same sign as the slope. If R is exactly equal to -1 or 1, then the dots are exactly on a straight line, and we have a deterministic relationship rather than a statistical relationship. If they're close to 1, it's a strong positive correlation. Close to -1, strong negative correlation. Close to 0, it might mean the dots are close to a straight line with slope 0, or it might be close to a curve that is not a straight line, or it might be there's no pattern. Anyway, these pictures kind of are some examples of what the correlation might be. Okay, so ours looks like I would say it's a strong positive correlation. if you want to call it a strong negative correlation, I mean, if you want to call it moderate positive correlation, I would accept that. But it has a positive slope. But the slope is positive as you go from left to right, and that means we think the dots are fairly close to a straight line. And let's see if we can draw that line. We want to draw a line through the dots. Usually some dots will be above the line and some dots below the line. So, you know, we don't want something like this because it doesn't match the slope. It has to match the slope. We have a positive slope here. We don't want something like this. It's too steep. We don't want something like this. It doesn't go through any of the dots. But anyway, we want something that's fairly close to a straight line. And let's see if we can sort of estimate the line here. I'll draw a to draw a line that represents the overall pattern of the dots. Okay. Okay, so I draw a line here that I think matches the pattern, and we can use this to write down the equation of the line. So I usually like to do pay attention to where it crosses the y-axis. So it crosses the y-axis. It looks like approximately -110. And the x-coordinate of that point is going to be 0. So this is would be a point on the line, 0, comma, -110. And we can call that x1, y1. And then we'd like to compute the slope in order to write down the equation. And for a second point, I like to pick a point that is not too close to the y-intercept, because if you put if you pick 2 points that are close together, then a small error here would result possibly in a larger error up here. So I like to pick the points that are a little bit spread out, and something that's easy to divide by. I think 40 is easy to divide by. So let's go up. See what happens when x is 40, see if x is 40. Go up to see where it hits the line. Looks like it's right about here. It doesn't have to be one of the original data points. It could be one of the data points. And let's see where it crosses. Okay, so it looks like this point here so the x-coordinate is 40, and y-coordinate, that's a little over 100. I don't know, maybe let's say 107. It's a little bit less than 110, a little more than 100, but I'll sort of estimate it 110, 107, and then we can call this x2, y2, and then we can use that to compute the slope. Okay, so I'll do that on the next. Okay, so the y-intercept, it looks like it's approximately -110. And the xy according to the y-intercept, the x-coordinate of the y-intercept is always going to be 0. So I put that up there. Actually, it's x1, y1, and then we want the coordinates of a second point, and our second point was 40, 107, and this is not an exact method here. We'll get into exact methods later, but I like the graphing method for finding the slope because it's I think it helps your intuition. So those are our 2 points, and then we can compute the slope. Mathematicians like the letter M for the slope. Statisticians like letters A or B. You may say B1 or an A. The calculator that I like to use uses the letter A for the slope. But anyway, it's going to be y2 minus y1 over x2 minus x1. So it's 107 minus a negative 110 over 40 minus 0. Okay, so double negative is positive, so this is going to be 107 plus 110 over 40. 40 minus 0 is 40. And then we can add these. This is going to be 217 over 40. And let's divide 217. Goes 5 times. 540 is 20. 540 is 200. 17, 0. 4 times. So approximately 5.4. 5.4, and it's going to be ounces per week. Okay. Okay, so then we can write our equation. It's the equation y equal ax plus b, or you can write it y equal mx plus b, or y equal b1 plus b0x. But anyway, we'll use y equal ax plus b. So the y variable is the birth weight, and the slope, let's say, is approximately 5.4, and the x variable is the gestation, and b is a negative 110. Okay, so that gives us an equation for predicting the birth weight based on the length of the pregnancy. Okay, so let's do find Quincy's predicted birth weight. So Quincy was born after 39 weeks. So if we use this equation here, so it's going to be the predicted weight is 5.4 times 39 plus negative 110. Okay, so 5.4 times 39, 5.4 times 39, 36, 5 times 9, 45, 48, 4 times 3 is 12, carry 1, 5 times 3 is 15, 16, and this is going to be 6, 10, carry the 1, 11, carry the 1, 2, 210.6, I can put it, 36. Okay, 210.6 minus 110. So that's going to be 100.6 ounces. So that's Quincy's predicted weight. And then Quincy's actual weight was 104 ounces. 104. So the actual minus, it's called the residual, actual minus the predicted. It's going to be 104 minus 100.6. It's 3.4 ounces, so it's off by 3.4 ounces. So that's Quincy's residual, or the prediction error, is 3.4 ounces. And sometimes they compute the squared residual. So the squared residual, 3.4 times 3.4, 4 times 4 is 16, 3 times 4 is 12, 13, 4 times 3 is 12, 3 times 3 is 9, 10, 6, 5, 1, 1, 11.56. So the squared residual is, or the squared prediction error, 11.56. Okay, so now the graphing method is not exact. When I did this before, I got a different slope here. I had a slope of 5.3. So I had, for Quincy, I had the predicted birth weight of 96.7, and then the residual 104 minus 96.7, 7.3, and then square that, you get 53.29. So that was a little bit further off. So this equation, when I did it before, I had a different equation. I was a little bit further off, but had a higher prediction error. So the graphing method is not exact. You may get a different answer. The answers can vary with the graphing method. So anyway, I computed the squared residual for each baby. So for each baby, I did computed the predicted birth weight, and then got the prediction error, or the residual, actual minus the residual, and actual minus the predicted, and then got the residual and squared it, and I got a and then the total of the squared residuals was 699. So that tells us, gives an idea. This total of the squared residuals gives us an idea of how accurate our prediction is. Also, this middle column here, the sum of residuals, if you have the best fitting equation, this middle column total should be 0. Our middle column total is not going to be 0 here, because we don't have the best fitting equation. And the best fitting equation also has the lowest last column, the lowest sum of the squared residuals. Okay, so here's a calculator program. We'll get into using the formulas to get the best fitting equation. There's also a calculator program that does that also, and it's this sequence of keys. You push clear while holding the on, and then clear, that clears out the data, and then you push second data, right arrow, enter, and then you put in the data for each of the babies, the 39 down arrow, 104 down arrow, and so forth. At the end, when you get the data in, push that far, and push the arrows over until you get the slope and the y-intercept and the slope. So these are the more exact numbers here. The slope, our slope, we estimated 5.4. This is a more precise number, 5.42857. And the y-intercept, actually our numbers were pretty close. Our y-intercept negative 109.7 something. So that gives you a more precise. This is actually the best fitting equation. We'll say more about the exact way of doing it, of getting the best equation in a different lecture, another different video. And that concludes this presentation.